So in this lesson, we're going to have a look at the Nernst equation, which falls under the umbrella of electrochemistry. So what we've done already is we've looked at how to calculate the cell potential, how to determine the cathode and anode, and obviously look at oxidation numbers and balancing redox equations. So we know that for any spontaneous cell, that Ecell will be equal to or greater than 0. So that means that when we're talking about spontaneity, we're looking for a delta G value to be less than 0. So delta G must be less than 0 and E cell must be greater than 0. So we end up having a negative sign in between to make sure that that does happen. So we are given this particular expression for calculating the free energy of an electrochemical reaction. So we say that Gibbs free energy is equal to the negative number of the electrons transferred times Faraday's constant, which is a conversion between moles and coulombs, and the EMF or cell potential. So we can start using this to determine exactly to what extent the reaction will proceed. So using standard cell reduction potentials, determine whether the following reactions are spontaneous under standard conditions. So that's the first thing that we're going to look at. So we have copper solid plus 2 moles of hydrogen ion producing 1 mole of copper ion and hydrogen gas. So the first thing we'll do is we will determine the oxidation states. So hydrogen is just a metal ion, so it's +1. This is neutral, neutral, and +2. So in this particular reaction, we're seeing hydrogen be reduced and copper being oxidized. So now we write out the exact expression that or half reaction that would give us that. So copper 0 goes to copper +2 plus 2 electrons. 2 moles of hydrogen plus 1 plus 2 electrons gives me H2 gas. So I have my two half reactions written out, and one of them must be an oxidation and one of them must be a reduction. So I have oxidation and reduction. So the first thing I will do is go and look up those particular values. Well, this here is the standard hydrogen electrode. So this by definition is 0 volts. We then look at Appendix E and we find the value for copper going to copper +2. Please remember that we are not looking for oxidations, we're looking at standard reductions. So you'll be looking for the reverse of this reaction, Cu +2 plus 2 moles of electrons giving me copper solid. And this is 0.34 volts. So we calculate a cell standard. So the cell potential is equal to the reduction potential of the cathode minus the reduction potential of the anode. E cell is equal to the cathode. So the cathode is where reduction is taking place. So that would be the more positive of the two. So in this particular reaction, it would want to be the more positive of the two, but it's not. So we have to go with what the reaction says. So when we look at this, we see hydrogen is being reduced, so we have 0 volts. Right off the bat, this is telling me that this reaction is not going to be spontaneous. So as we continue, is negative 0.34 volts. So this is, I know right away this is going to be non-spontaneous, but delta G is equal to negative NFE standard cell. So we're going to use this reaction. It's equal to the negative of the number of electrons transferred. So that is 2 times Faraday's constant, 96485 coulombs per mole, times Ecell 0.34 negative. So my number here is going to be positive. So I have 65 times 10 to the 3 joules. My answer will be in joules, or plus 65 kilojoules. So this is non-spontaneous. Delta G is greater than 0. So for the next one, we do the same thing, and you can see I've already started. We assign oxidation numbers, so we have our pure substances, iodine and chlorine, and we have our ions, which are just by themselves, so the oxidation numbers are very easy. We have chlorine going from 0 to -1. We have iodine going from -1 to 0, so we have reduction and oxidation. So we write out our half reactions. We look up the values for them. So chlorine is plus 1.36 volts. This is plus 0.54 volts. We get those values from Appendix E in our textbook. So now we need to calculate Ecell. So Ecell, just going to use this as the framework. Ecell is equal to the reduction potential of the cathode minus the anode. So the cathode is where reduction takes place. So I'm going to put chlorine, 1.36 volts, minus where oxidation takes place, 0.54 volts. Ecell is equal to plus 0 plus 82 volts. So this is a positive value, which tells me this is very likely going to be spontaneous. Delta G is equal to NF, negative NF Ecell. So it's equal to negative times the number of electrons transferred, which is 2, times Faraday's constant, 96485. Coulomb per mole, and 0.82 volts, and that gives me negative 158235 joules, or negative 158 kilojoules. So now that delta G is negative, we know that this reaction is spontaneous under these conditions. So for determining free energy, what you have to be able to do is look at the equation, sign the oxidation numbers, break that equation into two half reactions, one for oxidation, one for reduction. You then use Ecell under standard states to determine the cell potential under standard conditions. So that would be at when these substances are at 1 mole per liter and 1 atmosphere pressure. Once you have your cell potential, then you plug in your that into the equation. Faraday's constant is a constant, obviously, and n is the number of electrons that are transferred. Remembering that if the number of electrons aren't equal in your two half reactions, then what you have to do is you have to multiply those half reactions to get a common number of electrons between them, and that would be what your n is. When you solve for delta G, we know that delta G at greater than 0 is going to be non-spontaneous. At less than 0, it will be spontaneous. So that's the general idea of how we determine this. In these examples, we weren't necessarily looking at a cell where reduction was the more positive of the values. We were being told by whatever the reaction said what was being reduced. Sometimes when we're looking at a galvanic cell or a voltaic cell, you have to pick which is which is going to be the anode and which is going to be the cathode, and that is when you will pick whether you pick the most positive or not. So we can actually use this, since we can actually determine Ecell and to turn that into the standard Gibbs free energy. We can use what we did in Unit 12 or Chapter 19 in thermochemistry to actually calculate equilibrium constants. And we can also figure out exactly what the potential will be under non-standard conditions. So both of these things are very useful, and that's what the Nernst equation is about. So from Unit 12, we had these two equations where we had this one describing an equation not at equilibrium, and this one was at equilibrium. So literally exactly the same equation, just used in different situations, so we changed the name of them. When we put in this equation for delta G, we get this. The difference being standard state or not standard state. Sorry, standard state, not standard state. And we get this equation down here in the bottom that is in a box, and it says that cell potential is equal to standard cell potential minus RT over NF ln of the reaction quotient. So now we're starting to look at a combination of the last three units all in one equation. So we have electrochemistry, thermodynamics, and equilibrium piled into this question. So this is going to be called the Nernst equation, and this is what we're going to use to determine cell potentials in this section. So now we are ready to use the Nernst equation to determine exactly what the cell potential will be with using various situations. So it says, use the standard reduction potentials listed in Appendix E to calculate the standard free energy heat change, delta G, and the equilibrium constant at 298. We're going to assume that's 298 K. For the reaction 4 Ag plus oxygen plus 4 moles of hydrogen ion, producing 4 moles of silver ion and 2 moles of water. So we start by determining the half reactions, and that means oxidation numbers. So silver solid is as it appears on the periodic table, so it is 0. Oxygen as it appears on the periodic table, so it's 0. We have a metal ion by itself, so plus 1. Metal ion by itself is plus 1. And in water, we see oxygen as minus 2 and hydrogens as plus 1. So we look at this, we see oxygen being reduced, and we see silver being oxidized. So noticing that hydrogen stayed the same in this particular process. So now we write out our reduction and our oxidation. Our reduction is O2 gas plus 4H plus, which I have to include because I'm going to use water, and it's still got to be balanced, plus 1 electron produces 2H2O. So one of the biggest questions I get is, how do I know when to include H plus? And you include H plus in your half reaction because the compound in which oxygen is shown up as the reduced form has H in it. So I need to make sure I'm still balanced, as we've always done. And then you write your oxidation, 4Ag going to 4Ag plus 4 electrons. So when you look at your Appendix E for this, you're not going to find it with 4 and 4 and 4. You're going to find it with regards to 1, 1, and 1. And that's okay. Remember that cell potentials are an intrinsic property, so the amount does not matter. So our cell potential of this one, silver, is plus 0.80 volts. And of the reduction of oxygen, plus 1.23 volts. So again, that's what we've done earlier in the course in before in the first semester. So now we're just going to apply what we're doing now. So Ecell is the standard state reduction potential for the cathode minus the standard state reduction potential for the anode. So cathode is reduction, 1.23 volts minus 0.43 volts. So now we have standard cell potential. Again, it's the same method every time. So we go to the idea, now delta G equals negative NFE standard cell is equal to negative. So we look at the number of electrons transferred. It's not, I shouldn't have one electron here, I should have four. It is 4 electrons times 9, 6, 4, 8, 5. We can actually rearrange this this unit to be the joule, volt, mole. It's the same as what we've done before, but it's just a little bit easier to make it work. And then we end up with joules per mole in our overall answer, which some people like a little bit better. So this is equal to 1.70 times 10 to the 5 joules. And that's joules per mole. So it's equal to 170 kilojoules per mole. And we have our negative value here. Let's make sure we make that negative. So this is a spontaneous reaction under standard conditions. Now, delta G standard is equal to negative RT ln K. So let's plug in our delta G, negative 170. So using this G standard, we're going to determine the at least the equilibrium constant at this particular point. Ln K is equal to negative 1.7 times 10 to the 5 over 8.314 times 298. That's equal to 69. K is equal to e to the 69. K is equal to 9 times 10 to the 29. So under these particular conditions, we're going to see that the K is incredibly, incredibly big. Meaning that this is really not an equilibrium process, but the method that we're using does work for this. So one of the things that may confuse you is why delta G is being used as non-zero when we are solving for K. In this particular situation, we're using the delta G that this cell is going to produce, the free energy change, to calculate the constant at that particular moment. We could call it Q in this particular case. The naming is a little arbitrary, but the important thing to take away from this is that the constant that you're calculating is very, very big. and meaning that the one-way arrow up here is probably a very good representation of what is happening. So now we take the exact same problem, but we look at what happens when we write this with the coefficients halved. So the first thing that we should know right off the bat is that Ecell is going to be the same. Cell potential is an intrinsic property. It does not matter on the amount. So I'm not even going to do a calculation for that. Because if you look up, even if you were to take these values and cut them in half, the only thing that will really change is the thermodynamics of it, or anything that's an extrinsic property. But because these half reactions do not change, we don't really have to do anything. So Ecell is going to be the same. Delta G is equal to negative NF Ecell. So that's the same and that's the same. We look at N as the only other thing that could change. Well, if I cut these variables in half, instead of 4 electrons, I'm going to only have 2. So it looks like delta G will change by a factor of 2. So 2.96485 joule volt mole times 0.43 volts. And it's going to equal negative 83,000 joules per mole. So that did change. And because delta G is changing, when we figure out the law of the constant, since the numerator here is changing, we will solve and find that K is now equal to 4 times 10 to the 14. So it does change quite a bit between the two problems. So that is due, of course, to G actually having to change. So just a quick review. In this particular problem, we used oxidation numbers to determine the half reactions. We went to Appendix E and got our cell potentials. We calculated the standard cell potential based on the reduction in oxidation that the equation showed us. We calculated delta G into joules, but then converted it to kilojoules just for reporting purposes. We then used the equation from Unit 12 to calculate the standard free energy. To use the standard free energy to calculate the reaction constant, and we then looked at what would happen if we cut the coefficients in two, and saw that Ecell is unaffected; it's intrinsic by this, but delta G is affected because it's based on the number of electrons transferred, and of course that would affect K, which is based on that. So now we have to look at applying the Nernst equation to determine the amount of, given the amount of various components, and basically making it non-standard conditions, we're going to determine what the cell potential will be. And the method for doing this is very, very similar over and over again. First thing we do is oxidation numbers. So oxygens are -2. This is going to have to be +6 then, +1, -1, +3, 0, oxygens -2, making this +1. You got to do it every single time. There'd be really no exceptions to this in electrochem. Always going to end up doing your oxidation numbers. So we have reduction. So dichromate is being reduced. We have chromium going from +6 to +3. That's a reduction. I'm going to look at Appendix E look for dichromate and find my appropriate reaction. meaning the oxidation is going to take place, it looks like, of iodine. So 6 moles of I minus, just writing it from the balanced equation above, gives me 3 moles of I2 plus 6 electrons. You can tell it's already been balanced because the electrons are working out well. The standard cell potential is equal to the reduction potential at the cathode minus the reduction potential at the anode, Ecell. So, you should probably get these values. The reduction potential for this is 1.33 volts. The reduction potential for this is 0.536 volts. So the cathode has reduction, so 1.33 volts. Anode has 0.536 volts. Do our calculation. E cell is equal to 0.794 volts. So we're just going to write, we have the overall expression, which is what we need, and we're going to write the reaction quotient of it. So water and iodine are solids, or solid and liquid, so they don't appear in this. So I end up with chromium plus 3. The coefficient's 2, so I'm going to square it. Dichromate, H plus to the 14th. It's a nice big number. And iodine to the 6th. So I end up, let's just plug in our value. So chromium is 1.0 times 10 to the negative 5. And we square it. Dichromate is 2. Hydrogen ion is 1 to the 14. Iodine is 1 to the 6. Trying to make our lives a little bit easier, I think. Q is equal to 5.0 times 10 to the negative 11. So that's the work that we've kind of already been looking at. Now we're going to go to the Nernst equation. So the Nernst equation is E equals E standard minus RT NF ln Q. Well, in situations where RT and F are constant or at 298 Kelvin, we can actually convert this. And also, we're dealing with natural logarithms, so we're going to actually deal with that too. We're going to just make the conversion to a base 10 logarithm, and then kind of blend the rest of this together. So we can, when we do that conversion, and this is always the same, we get 0.0592 over n. The unit on this is technically the volt, and we end up with log Q. So we've basically, in the 0.0592, we've blended those three together and then done the conversion from ln to log. It doesn't necessarily need to be ln to log, but this number is, what we're given. So the conversion's already done for us, so we don't really have to worry too much about it. So the non-standard cell potential is equal to the standard cell potential minus 0.0592 volts over the number of electrons transferred, which is 6, and the log of 5.0 times 10 to the negative 11. E is equal to 0.794 under standard conditions, and then a little correction works into plus. So we can see that under these conditions, this reaction becomes more favored. So the standard cell potential was 0.794 volts. We got that up here. Minus 0.0592 volts over the number of electrons transferred, and that is 6 times the natural logarithm of this. Standard cell potential is equal to 0.794 4 volts minus, when you solve this part of the equation, you end up with basically plus 0.10 volts, equals 0.89 volts. So under these conditions, the voltage will actually be higher in this particular problem. So again, a summary: get your oxidation states, redox equations or half cells. If you're stuck, look at the appendix E to try and figure out what goes with what. Look at Ecell, calculate your standard state. Given these concentrations, calculate your Q. Then use the Nernst equation to calculate the non-standard cell potential. So if the voltage of a zinc hydrogen cell is 0.45 at 25 degrees Celsius, when zinc is 1 mole per liter and the pressure of hydrogen is 1 atmosphere, what is the concentration of H+? So we have our equation. We have 0 plus 2, do our oxidation states, plus 1 and 0. So I'm looking at this and I am seeing the standard the standard hydrogen electrode. So zinc going to zinc plus 2 electrons, 2 moles of hydrogen. So by definition, this is 0 volts. We look up zinc and we get negative 0.76 volts. So again, we're going to keep doing it, but what we're looking at is do your oxidation states, break them into the half reactions, break it into I have oxidation and reduction. These are still the reduction potentials, even though this is written as an oxidation. I don't bother changing that. The equation takes care of that for me. So Ecell is equal to the reduction potential at the cathode minus the reduction potential at the anode. Ecell is equal to the cathode where reduction is taking place, which is hydrogen, and where zinc is negative 0.76. So we have a positive cell potential, indicating that this is a spontaneous reaction. We look and figure out what is the number of N, the number of electrons transferred. It is equal to 2. So we now go to the Nernst. Standard cell potential is equal to standard cell potential minus 0.0592 V over N. And we have log Q. So what we are looking at here is the Nernst equation at 298 Kelvin. So make sure that you are at 298. There's 25 degrees Celsius or 298 Kelvin. You'll also notice that we are dealing with the log of Q, not the ln of Q. When we take this into account, we correct for, we don't want to use Euler's number, so we use base 10. So we're basically going to rearrange this and solve for the log of Q. So log Q is equal to E minus E0 and N over is equal to 0.76. So we can go through and calculate our Q value. So um, while we look at this, these should be reversed. There should be a negative here, but when these are reversed, we see that Q is equal to 3 times 10 to the 10. We write our expression for Q. Q is equal to zinc plus 2, the partial pressure of H2. So we're going to cheat a little bit and use pressure in with this Q expression, because assuming we're under standard conditions. We solve our Q. Concentration of H plus squared is equal to 3 times 10 to the negative 11. Concentration of H plus is equal to 6 times 10 to the negative 6, giving us our value for H plus. So we have the value for H plus, and what that kind of means for us is that we could theoretically calculate the pH of this solution required. The other questionable part that we're looking at here is the presence of the partial pressure of H2 in the equation. We're assuming that based on the assumption is that based on what we're doing, that the difference between pressure and the number of moles is not really going to have a huge effect on that constant. It's not going to affect the equation a lot. So it's an okay assumption to make here. Now, we've been talking about electrochemical cells where we have a unique species being oxidized and another species being reduced. Concentration cells are when you're using the same substance in both your anode and cathode, just at different concentrations. So what we have here, and just looking at this example, this diagram, is that when you use nickel at 0.5 moles per liter in both sides, the cell potential is 0 because there's really nowhere for anything to go. However, if you use one that's a lot more concentrated than another, you will get a very, very slight voltage change. The current will flow. We call this a concentration cell. So let's do a few calculations here. We're looking at this nickel cell. So at the anode, where we are going to have oxidation, we say we have nickel solid going to nickel plus 2 electrons. At the cathode, we write the reverse of that. The standard state reduction potentials for both is equal to 0.28 volts. So I have anode cathode, so that makes Ecell is very simply equal to 0 volts, the same. Well, when we alter the concentrations, basically what we do is we create an imbalance where the cell will actually start working and to try and restore that balance, in other words, to equal the concentrations. So in a concentration cell, we say that we have nickel solid going to nickel plus 2, and this is aqueous, and we're going to call this the dilute, plus 2 electrons. At the cathode, we're going to have nickel plus 2, aqueous, concentrated, plus 2 electrons, giving me nickel solid. Now, for the dilute, we're looking at 1.0 times 10 to the negative 3 moles per liter. And for the concentrated, we're looking at 1 mole per liter if you looked at the diagram. So overall, when we add these reactions together, the solids are going to cancel, the electrons will cancel, and we end up with an expression that says nickel plus 2 of the concentrated going to nickel plus 2 the dilute. And those are both aqueous. So it's a very strange electrochemical reaction, but because the concentrations are different, we are going to write it out like this. So we're going to use the Nernst equation to try and help us solve this problem. When we use the Nernst equation, we are creating a new law in Q, which makes this matter, which will make E slightly different than E standard, which would normally be 0. So when we solve it, we get the 0.088 that the diagram shows. And that's just by plugging these values in for long Q. So for the nickel one, we would say E is equal to 0 volts minus 0.0592 over 2 log of the product. So nickel plus 2 dilute over nickel plus 2 concentrated, which would be 1 times 10 to the negative 3 over 1. E is equal to 0. Minus 0.0888 volts equals plus 0.0888 volts. So that's how we get that calculation done. Very, very small voltage, but it definitely is not 0. So let's look at how we can apply this to a real problem. A voltaic cell is constructed with 2 hydrogen electrodes. Electrode 1 has a partial pressure of H2 at 1 atmosphere and an unknown concentration of H+. Electrode 2 is a standard hydrogen electrode where H+ is equal to 1 mole per liter. Pressure of hydrogen gas is 1 atmosphere. At 298, the measured cell voltage is 0.211. The electrical current is observed to flow from electrode 1 through an external current to electrode 2. Calculate the H+ for the solution at electrode 1. So we're going to start with this equation. We're going to start with the Nernst equation. We know the cell potential is E is 0.211 volts. We know that since it's the same electrode on both sides, that under standard conditions, it would be equal to 0 volts. Minus 0.0592 over the number of electrons. So if you look at the standard hydrogen electron, you have 2H plus 2 electrons going to H2 gas. So the value for N is equal to 2. And then we're multiplying this by the logarithm of Q. Log Q is equal to negative 0.211 volts times 2 over 0.0592. And this is equal to negative 7.13. So log Q is equal to negative 7.13. Q is equal to 10 to the negative 7.13. Q is equal to 7.4 times 10 to the negative 8. So before we continue, we should really make sure that we know what's happening at electrode 1 and electrode 2. At electrode 1, we have hydrogen gas at 1 atmosphere going to 2H plus. It's aqueous. We don't know the concentration. Plus 2 electrons. At the other one we have oxidation taking place. This is the anode, so we have current flowing from electron 1. So you can see how I know that is happening. It's flowing from anode 1, which means it's flowing from the anode. So I know that electrode 1 is the anode. So 2H plus gives 100 molars. That's given to us in the question. Plus 2 electrons gives me H2. And making this the cathode. So these are both the standards hydrogen, so we know we're at 0 volts. But when we add these up, that's where this becomes a little bit more interesting. So when we do the Q for this, we're going to have products over reactants. So the first product that we're going to have is this. So the concentration of H plus, I'm going to write X next to it, unknown, squared, times the partial pressure of H2 and this is for electrode 2, and this is the partial, this is H plus, and this is the electrode 2 one, that 1 molar squared, the partial pressure of H2 for electrode 1. So this is equal to X squared times 1 over 1 squared times 1. So again, we're getting away with the partial pressures simply because of the ones. And we know that Q is equal to 7.4 times 10 to the negative 8. So now we rearrange and solve for x squared. Well, these ones are useless. So we take the root of both sides. X is equal to, x squared is equal to 7.4 times 10 to the negative 8. X is equal to 2.7 times 10 to the negative 4 moles per liter. So I can calculate the pH of that. The negative log of that number is equal to 3.57. So again, we're just using the same approach. The part that really is different is here. But again, you're writing your anode and cathode, and they're giving you a word problem and telling you what is the anode and what is the cathode. You write the equation out exactly as it was before, paying special attention to what is different. We could have eliminated the gases from the overall reaction, and we wouldn't have really noticed any difference at all. So now that we've dealt with concentration cells, we're going to look at something called electrolysis. So we know that when an electrochemical cell produces an Ecell standard less than 0, that it's not spontaneous. We can make these processes take place if instead of expecting electrical current, we apply electrical current, and we call this electrolysis. So let's look at molten sodium chloride to produce sodium metal and chlorine gas. This is definitely not something that's going to happen easily. So if we apply current to this process, we can actually make it happen. That's all electrolysis is. So it's basically you have the reverse. You know that under standard conditions delta G is going to be more than 0. So you know it's non-spontaneous. Now we're just basically looking at how are we going to make this take place. So I think the best way to go through electrolysis is actually through an example. So we have a try this here. It says calculate the number of grams of aluminum produced in 1 hour by the electrolysis of molten aluminum chloride if the electrical current is 10 amps. So first of all, before I even say anything, if you haven't taken physics, 10 amps is equal to 10 coulombs per second, and a coulomb is 6.18 times 10 to the 18, sorry, 6.24 times 10 to the 18 electrons. And that's, again, not really relevant because that's what Faraday's constant's for. It converts between moles and coulombs. So we have the overall reaction. So we know that aluminum here is plus 3, and we know that aluminum here is 0. We know that chlorine is minus 1, and we know that chlorine here is 0. So chlorine is being oxidized. So Cl minus so we have our oxidation. And I am oversimplifying this because it is a molten, it's not going to dissociate, but we're just going to make sure that we understand what's happening here to simplify it. So we have an oxidation and reduction. We know that we're going to need 3 moles of electrons to reduce aluminum, and that's why I'm writing that out. It is molten, so it's not dissociating. So the first thing we want to do is figure out how many coulombs of electrons we have. So the first thing we'll do is determine the number of coulombs. So the number of coulombs, which is just a packet of electrons, is equal to the electrical current, symbolized by the capital letter I, times T. So that's equal to 10 amperes, so 10 coulombs per second, times 1 hour, times 3600 seconds per hour. So that's equal to 3.6 times 10 to the 4 coulombs. So the next thing we're going to do is figure out how many moles of electrons that is, because we are doing chemistry. So we do that by saying 3.6 times 10 to the 4 coulombs times Faraday's constant, so 1 mole of electrons is 96485 coulombs equals 0.373 moles of electrons. Now we do stoichiometry, that's all that's left. So how many moles of aluminum do we need? So I have 0.373 moles of electrons times 1 mole of aluminum over 3 moles of electrons, 0.124 moles of aluminum. So now I have moles of aluminum. And the final thing we'll do is grams of aluminum is equal to 0.124 moles of aluminum times 27.0 grams of Al for 1 mole equals 3.36 grams. So we will get 3.36 grams. When you're doing this question, probably the only thing that seems to catch people is remembering to do the conversion of moles of the substance to the number of electrons required to form that. So you've got to do that, otherwise you'll get only a third of what you should have had.